Okay, so the problems you've been working on are in particle kinematics along a line. And I was asked about number 6. Um, so a ball's thrown into the air from a starting height of h. So here's the ground. And it's thrown from here, and it reaches a high point of h max. So it goes straight up and straight back down. This distance is h. And this distance to the highest point is h max. And based on those, we need to calculate the initial speed of the ball. The velocity when it reaches a height h on the way back down. The velocity the instant before it hits the ground. So just before it hits the ground. And then the last one is show that for any free fall problem, the speeds are the same. At the same height, whether it's going up or coming down. All right, so this is just like the other problems we've done, the example problems I've done. The only difference is we're using, variable expressions instead of numbers. So I'm going to call, so we already have h and h max. I'm also going to use this constant g as equal to 9.81 meters per second squared. And for a zero position, I'm going to do, just because I always do it, I'm going to put my zero position on the ground and my positive direction up. And for A, my time equals 0 instant is going to be when it's released. And my time t is going to be, okay, so how are we going to choose where the time t is? The time equals 0 is when it's thrown. The time t has to be based on where we're trying to calculate stuff and where we know stuff. The stuff we're trying to calculate is at time equals 0. Okay, probably more often than not, it's at time t, but in this case, we're trying to calculate the velocity at time equals 0. So now we're looking for another later instant where we have information. What are we gonna, so what's gonna be our choice for time t? Yeah, right, we wanna choose the instant when it gets to the highest point, because when it gets to the highest point in this problem, we know two things. We know the height, so we can come up with the position. And we also know the velocity, because when something reaches its highest point, its velocity is 0. Okay. So time t is going to be the instant that it reaches its highest point. And now we can think about, out of these variables, t, a, p0, p, v0, and v, we can think about which ones we know, which ones we're trying to calculate. We don't know the time. We don't know how long it takes to get to the highest point. We know the acceleration is downward at 9.81 meters per second squared, or in other words, downwards with an acceleration of g. So is that a positive or a negative g? Negative, yep, because our positive is up. I'm going to call that negative g. Our p sub 0, well, we know that at time 0, the height is h. So what's the position given our 0 position at the ground and the positive direction up? Yep, positive h. Do we know the position at time t? Yep. And then v sub 0 is what we're trying to calculate. Do we know v? 0, yep. And so now we're looking for an equation that has these. Well, it looks like we can use, it feels like we've used this one most of the time so far, but we can use this equation that says 2a times the quantity p minus p0 is equal to v squared minus v0 squared. So that says negative 2g times the quantity, and I'm just replacing the variables in this equation with the constants here. So P is H max minus H is equal to 0 squared minus V0 squared. You can divide both sides by -1, and you get 2g times the quantity H max minus H is equal to V0 squared. Take the square root of both sides, and you get that V0 is equal to plus or minus square root of 2g times the quantity H max minus H. And do we want the positive or the negative? Well, we're not calculating time here. So you need to think of a different reason. It is the positive one that we want. A positive velocity at the instant it's released. It's thrown up into the air. The negative represents that would be the speed on the way back down. Okay, so that's the answer for the speed, the velocity at the instant that it's released. If you were asked for the speed is just always positive. It's the absolute value of the velocity, but the velocity can be positive or negative. Any questions about that part? Okay, well, the next thing we want to know is the velocity when the ball returns to that height h. Well, we talked about this yesterday. It's just a fact of free fall that the speeds are the same at a given height on the way up that they are on the way down. So when it returns to a height of h, the velocity is going to be this, but just negative. Okay, that's the way it always works. But you can calculate that by setting, so for part B, write out these variables, TA, P0, P, V0, and V. And now we need to change the meaning of the time t. The time 0 can have the same meaning, but the time t has to refer to the instant that it falls to a height of h0. Please stop me if you have any questions about any of the choices I make here. We still don't know time. The acceleration is still negative g. P0 is h. This time p is also h. V0 is this ugly thing. That's the positive square root. And we're trying to calculate this v. So again, I can use this equation that says 2a times the quantity p minus p0 is equal to v squared minus v0 squared. And so we get negative 2g times the quantity, well, these are both h. And so this is equal to v squared minus v0 squared. Well, we can write that as minus the square of that square root is 2g times the quantity h max minus h. This side goes away, and you get that v is plus or minus square root of 2g times the quantity h max minus h. So this represents the velocity of the ball when it gets to a height h on the way back down. Do we want positive or negative? Negative because it's on the way down, which is opposite what we chose as the positive direction. Any questions about that? Yeah.
What happened to the 2g on the left side?
The 2. Oh, yeah, right. H minus h is 0, so the whole left side goes away. Any other questions? That's right. And since v naught is squared, the square root goes away. Yep. Okay, and now calculate v just before it hits the ground. Well, there's two ways you can do this. You can call your t0 the instant that it reaches the highest point, and your t the instant right before it hits the ground. Or you can keep your t equals 0 the same as it has been. Either way, the t has to be right before it hits the ground. Okay. Well, let's choose our time equals 0 this time to be when it reaches the highest point. It seems to me like this will probably give a little bit less simplification when we get to the final answer. The final answers have to be the same, but it seems like we'll start out with an uglier expression for it if we start with time equals 0 where it's thrown, when it's thrown. So time equals 0 is when it reaches the high point. Time t is just before it hits the ground. And then same thing, we have to figure out what we know out of t, a, p0, p, v0, and v. We still don't know time. It's still free fall, so this is negative g. P0, what's P0 this time? What's the position when time is equal to 0? That's right, it's H max. And what's the position when time is t? 0, yep. And what's the velocity when time is equal to 0? 0, because our time equals 0 is when it's at the highest point. So the velocity has to be 0 at that instant. That's the thing that makes me think this is probably going to look a little nicer than what we would start out with going the other way. And then we're trying to calculate this v. Yeah, yeah, think about it that way. It's
basically like a limit. It's infinitely close to it.
you know, like, yeah, there's some stuff that you would have to think about. Like, are you talking about when the ball's thrown? Are you talking about where the bottom of the ball is? Is it a height of h? Or are you talking about where the center of the ball is? And then when it hits the ground, you know, normally when you're talking about particles, the location is the center of mass. So you'd have to calculate how big the radius of the ball is and subtract that from the height and stuff. So in a way, yes, this is all approximations, assuming the ball is tiny. You know, we're treating it like it has 0 size. So yeah, you could think about some stuff like that, but it's fine to do it this way. All right, so we're going to use the same equation again, and we get negative 2g times the quantity 0 minus h max is equal to v squared minus 0 squared. And so you get that v squared is equal to, those two negatives cancel when you distribute it through, and you get 2g h max. Take the square root, and v is equal to plus or minus square root of 2g h max. This is representing the velocity right before it hits the ground. So is this v positive or negative? Negative, because it's on the way down, which is the negative direction. If you did it the other way, you'd get the same thing, but it might not be super clear at first. It would take, I think, a lot of simplification, but eventually you would get that. And then the last question is to show that at two different, so let's say at a height, I'll call it capital H, on the way up and down, show that the velocities are equal and opposite, show that the speeds are the same. Okay, so our time equals 0 is going to be when it reaches the height h, capital H, on the way up. Our time t is when it reaches the height h on the way down. And so now let's think about what variables we know and what variables we want to find. T, A, P0, P, V0, V. It's free fall, so A is negative G. At time equals 0, the height is capital H. At time t, the height is capital H. And let's just fill this in and see what we learn about these two. So if we go to this equation, 2a times the quantity p minus p0 is equal to v squared minus v0 squared. You get negative 2g times the quantity capital H minus capital H is equal to v squared minus v0 squared. The left side goes away because those heights are the same. And so v squared is equal to v0 squared, which means their magnitudes are the same. The only thing that is different is the signs. Any questions about any of those? So what it asked you to calculate is to show, it asks you to show that for a free fall problem, the speeds are the same for any chosen height. So I just made up this new constant capital H, and I said that's the height that we're specifying, and then did everything based on that. Any other questions? Yes? Yeah, I could give you a question like this. I think you should, be comfortable with both of those two ways of doing it. Yes?
Would it be okay to represent this in a graph and then explain the graph, but the slopes are the same on each side?
Yeah, that'd be fine. Any other questions? Yeah.
Would we ever have to do something similar on a test, kind of questions that we
Yeah, let's see, there is a problem like that, right? Any kind of problem that's on the homework, you can expect that to, be on a test. But if there's stuff that I talked about in class that is unlike anything that's in the problems, that you don't have to worry about. And that just means that I talked about it in lecture to try to make a point about something else. But the test problems will always be the same thought process. Any other questions about this? Any other homework questions you want to see? Yes. Sure. Here. Thanks. All right. So the next thing we need to talk about is relative motion. So we'll go back to new material. And this is relative motion. Okay, so say you have this object that's moving along a line. And you want to track the motion of that object. I've been talking a lot about the point that before you can measure where that object is at a given instant, you have to choose a 0 position and a positive direction. Okay. So to track this object's motion, numerically, you need to choose a positive direction and a 0 position. So imagine that 2 different independent people are tracking the motion of this object. People track the motion using different 0 positions. Although it's important to recognize that for this stuff, the positive directions have to be the same. So the question is, how do their different, those 2 measurements of position compare to each other? How do the 2 measurements of position compare, relate to each other? All right, well, let's say that one of these has its 0 position here and its positive direction that way. Okay, I'm going to call that reference frame A. And then the other one has its 0 position here. Positive direction has to be the same, and I'm going to call that reference frame B. Okay. What we want is a mathematical way to relate what the person at A sees so that the person at B could always calculate what's going to be determined, what's going to be seen from A. Okay. So to do this, we're going to use this naming convention. So the position naming convention we're going to use is that the position of, I'm going to call, well, it's a car, so I'm going to call it C for car. So position C, like fraction bar A, okay, so that's all a subscript, C over A. I'm going to call that the position of C relative to A. Okay, so that's the position that's observed to someone with their 0 position at A, and the position of C relative to B, or, C over B is what the subscript looks like, and I'm going to call that the position of C relative to B. And the relative motion equation for position, then, this is always true. The position of C relative to A is equal to the position of C relative to B plus the position of B relative to A. So the position of B relative to A is saying, for the person who's observing this motion with their 0 at A, what would they say the position of B is? Okay. So this is our first relative motion equation. And if you look at these answers, like what I drew here, say these are 10 meters apart, say it's 5 meters from B to the car. Okay. It's saying that, so this is 10 meters, this is another 5 meters, right? So it's saying that the position of the car here, observed by A, well, what is it? What's the number? It should be 15, okay? So it's saying that the position of the car observed by A should be equal to the position of the car observed by B. What's that number? 5, plus the position of B observed by A. What's that number? 10. So it makes sense that that works out, right? It's not always going to be called A, B, and C. These subscripts will have different names based on what you're tracking and whatever. So there's a memory device that'll always let you get the subscripts in the right order. And it says, think of the subscripts as a fraction multiplication. Then the order of the subscripts is right when the fraction multiplication works out. Okay, so what I have here is C over A is equal to C over B times B over A. The B's cancel. And so you know that you have this in the right order. Okay, any questions about that? Okay, well, this gets more interesting and more useful if those 0 positions are not just sitting there on the street, but they're actually moving around as time goes by. Okay. So those 0 positions can also be moving. Yes. They don't have to be. One could be still and one could be moving, or one could be going the other direction. Okay. But if you take the time derivative of both sides of that first equation, time derivative of each side of the boxed equation above you get d dt of the position of of C relative to A is equal to d dt of the position of C relative to B plus d dt of the position of B relative to A. Well, these are just velocities. So you can think of this as the velocity of C that's observed by A is equal to the velocity of C that's observed by B plus the velocity of B that's observed by A. And so there's the velocity relative motion equation. And that subscript rule still has to work. Okay, I didn't change anything about the order of the subscripts. And then you can do it again and you get the acceleration version of this. And so the last one says the acceleration of C relative to A is equal to the acceleration of C relative to B plus the acceleration of B relative to A. So those three boxed equations are the relative motion equations. Intuitively, think of each zero position as a video camera or an observer. Okay, so think of it as either a person represented by B moving around, or they don't have to be moving around, or a video camera that's moving around on like some kind of cart. Okay. Then based on what's observed by one of the video cameras or one of the observers, you could calculate what the other video camera is going to see. Okay. And one thing that's sometimes helpful is if you ever have the right subscripts, but they're in the flipped order, okay? You can flip the subscripts if you just make the whole thing negative. So I'll do it with position too. So position of A relative to B is negative position of B relative to A. Velocity of A relative to B is negative velocity of B relative to A. And acceleration of A relative to B is equal to negative acceleration of A relative to B. Okay, so let me do an example problem. Does anyone have any questions yet? Yes. Dang it. B to A. Thank you. Yes. Not necessarily. They could be that they would be shifted off from each other if they're both moving in sync with each other. But if one's still and one's moving, then no. So not necessarily. Any other questions? Yeah. No, I mean you can always get away without doing it, but sometimes you'll write it out and then you'll say like, you'll have it and like, oh, if I only had the sign switch, this would work. So then that's sometimes a useful tool. All right, so let me do an example, and it'll sort of point out cases where, like, what's kind of the practical application of this. All right, so first of all, an elevator. So think of what an elevator does. So you get on the elevator and it's still, okay? And then it takes you up or takes you down. Before, most of the time that it's going, it's moving at a constant speed. Okay, so on the way up, most of the time you're just going like 3 meters per second up or whatever. But right at the start, there has to be a period where you're going from rest to 3 meters per second. And so right at the start of that motion, you accelerate for a second or something. And you can sense that. That's the feeling that you get when the elevator starts to move. You can sort of feel it in your stomach. That's what you're feeling is the acceleration. Okay. And then it goes away once you get up to speed. You all know what I'm talking about? Okay, so let's say that an elevator is accelerating up when a passenger drops his keys. A video camera, like according to a video camera in the elevator, it shows the keys accelerating down at 12 meters per second squared. What's the acceleration of the elevator? And I should say, for these early problems, this relative motion thing is going to be important in this class. For these early problems, a lot of you probably can just sort of work it out kind of by feel and get it right. But get in the habit of writing it out in terms of the variables and the subscripts, because you're going to need to do that later. Okay. Okay, so here's what's going on. We have this elevator. And here's the key. The key is falling. So I'm going to call the key K. The camera in the elevator, I'm going to call E. Okay. So whatever that sees, that's the measurement taken by E. And I'm going to call my positive direction up. Remember, the positive direction has to stay the same for both of your two measurements. And then I'm also going to have a reference frame that's fixed to the ground. So let's say this is the elevator shaft. You can imagine there's also a video camera that's fixed to the ground. I'll call that G. Okay. All right, well, we're dealing with accelerations, so we want to use the acceleration equation that says the acceleration of the keys relative to the ground is equal to the acceleration of the keys relative to the elevator plus the acceleration of the elevator relative to the ground. Okay, are you with me on that? And this is the one that we're trying to calculate. We're trying to calculate how much is the elevator accelerating according to the camera that's mounted to the wall. Okay, well, this camera that's mounted to the wall, even, and by the way, these can be imaginary. It doesn't say anything about there being a camera mounted to the wall of the elevator shaft. But if there was a camera mounted to the wall of the elevator shaft that could see the keys, what would it see the acceleration of the keys to be? Exactly. So we have negative 9.81 meters per second squared because the keys are in free fall. Okay. What's the acceleration of the keys that's seen by the elevator? Yep, and it's down, so it's negative. So negative 12 meters per second squared. And then this is what we're trying to calculate. And so now it's just algebra, and you get that the acceleration of the elevator relative to the ground is equal to positive 2.19 meters per second squared. That was given. It says the camera in the elevator, you take the measurements based on the video you see, and it looks like it's accelerating down with extra acceleration. Any questions about that? And you can use this to explain, I'm sure there's a problem like this. I can't remember exactly. Yes. Oh, yeah. But, you know, that, so like you're driving your car and you slam on the brakes and you have your coffee sitting on the dashboard or on the console or whatever, okay? You slam on the brakes. To an observer in the car, where does the coffee go? Yeah, to an observer in the car, the coffee looks like it all of a sudden accelerates forward and slams into the dashboard, okay? To an observer on the street, if the car was glass, which is not a good idea, what they would see is that the coffee cup is moving along, and all of a sudden the car stops and the coffee cup just continues in projectile motion. Okay, it doesn't have any forward acceleration. The only acceleration it has is the downward acceleration of gravity, and it just continues the same way as if you had thrown it forward. Okay, but that can all be explained by this relative motion stuff. Okay, that's all.
Just make the card a clear plastic instead of glass.
No, glass.
Might be a little safer.
No, glass.
Oh, okay.
Okay, has to be glass.
Okay. Much safer.